What's up, coders? Today we're playing the role of librarians, not with actual books, but with elements of an array. Continuing the theme of this sorting series from the bubble sort, we're going to be diving into, you guessed it, the selection sort. It's a simple and intuitive sorting algorithm that works much like organizing books on a bookshelf. It's a classic that's pretty vital for a solid, fundamental understanding of sorting algorithms, just like our bubble sort video was, which will be linked in the description down below. And it's the previous video in this playlist if that's easier for you to find it that way. So fasten your thinking caps, because by the end of this video, you're going to be selecting elements like a pro. And remember, we're just sorting through things together in this coding journey. So let's dive on in. This selection sort is going to act kind of like an analog to the bubble sort, where the things bubbled towards the top. We're going to be doing the opposite. Again, we're going to be using our bookshelf analogy that we discussed in the previous video, where we have books of different sizes representing the different elements of an array. We want to organize them from smallest to largest, just like any sorting algorithm will want to do. In the selection sort, we start at one end of the bookshelf, say the left, and we're going to scan all the books to the right to find the smallest one. So we're going to keep track of what our smallest book so far has been. And that process of walking along the bookshelf and picking up each book to check to see if it's the smallest one you found so far is what our code is going to do. Once we've looked at all of the books on the bookshelf, and we've confirmed that we have the smallest one we've seen so far, we move it to the far left-hand side of the bookshelf, to the spot where the first book was initially. And then after that, that's the selection part, right? Where we select the smallest item and put it in its final place in the sorted portion of the bookshelf. Now we just ignore that first book, so like our outer loop, and then, because it's already in its final position, and then we start at the second to last book at the end of the left, and then do the same thing over again. Compare and look at every single book to find our smallest, put that in the second spot, then move to the third spot, and look onwards and continue until we have our sorted bookshelf. And that is exactly what we're going to do with our array. So, the selection sort. Like I said, these are fairly straightforward, my little sorting series here. These are not so much, you need to memorize these from top to bottom, but you need to be able to understand how to discuss them in an interview setting. Like, again, the chances of you actually having to write them, but being pop quizzed to see if you know some of the differences between the common sorting algorithms, pros and cons, comparisons, big O's, are pretty likely in beginner interviews, especially if you're interviewing like in an enterprise level place. So these are just like classic gotchas that I want to make sure you pass and not just flounder around on. So coding this one out, just like before, is not too terrible now that we're gonna know what our goal is, sorting an array of elements, in this case just integers. And then we're going to have to be clearly looping through all the books more than once. So that sounds exactly like what we learned in the previous video, where we have a double for loop happening here. Our outer for loop will be in charge of starting on the left-hand side of our bookshelf and going to the very end while looking for our smallest. Or rather, my apologies, the outer loop will be the one that will, for each book that we place, move on to the next iteration until the whole thing is sorted, right? So outer loop, start at the left-hand book and look, and then the inner loop will go through all the other comparisons, trying to find the smallest, and then place it. Then the outer loop will go to say, hey, starting at the second book and onwards now, compare that. So that's what's going to be happening here. So we'll just use I as our iterator in this case. Let I equal 0. It'll start at the left-hand book. Just like in the previous one, I'm also going to choose to make a variable that will represent the array length, just for some clarity, just because we're going to be using it more than once here, so we can just calculate that right there. Just as a variable once and not make a calculation per iteration. So we can say as long as it's less than the length of our books on the bookshelf, we're going to keep incrementing by one individual book. So at the very beginning, we'll just say that we're going to make the assumption that the first book we encounter will be at that position I, right? Like we're going to say, hey, this is the first item of our unsorted segment is going to be the smallest. We're going to make that assumption, and then from there, just start comparing to see if it is the smallest, like meaning it's already sorted, or find something smaller and then say, oh, this is the new minimum. And there you go. So from there, we're going to have a loop that will now make a comparison for every other part of the array to see if everything of our current minimum is smaller or not. So we'll use the iterator j, and j does not need to always start at 0, because once we have our first book placed, we can start at 1 and onwards. And then once we have our second book placed, we can start at 2 and onwards. So rather than having a numbered assignment here, we're going to simply say be one higher than whatever I currently is, because I represents, again, like that outer loop going, okay, the smallest book, then the next smallest book is organized, and the third smallest book is organized. And I increments over time, which means we'll simply look at one further than i's current position, because the one before it is technically already sorted where it should be. And then from there, we're going to simply go so long as j is less than length, and then increment j by 1 each time. Again, this is comparing every other book to see if it's smaller than our minimum or not. And we're going to say if the book at position j in this inner comparison array is smaller than our current minimum, then we have a new minimum we need to set. So we're going to say min is now going to be the index of j in our bookshelf. So what this is doing for us, once again, is like this made the assumption, and we're not storing, as you can see, the element, but we're storing the position of the element, or book on the bookcase, however you want to think about it, of where it is, right? So we're going to say, hey, at our current comparison on the bookshelf, if that element value, if that book is shorter than our current shortest book we've seen, then we're going to say, hey, this is the new shortest book we have seen in this position. After that inner for loop is done, it's time to swap. We're going to say, if the minimum does not equal I, for example, so we're going to say, if it's not currently the smallest book, meaning somewhere inside of here the comparison has set a new minimum and it's not equal to the current position, which would be 0, then 1, etc., meaning clearly it has moved since we've set it on line 15, we will then say to do our swap. And we can do that with a classic temp swap, where we can say if ri goes into temp, the new ri becomes the new rmin. I'm pretty sure I'm doing this right. And then the new rmin becomes the temp since we reassigned it. And that's like your classic array swap right there. Just go to swap positions. We did that in the bubble sort video as well. So from there, we're going to console log the array and return the array for testing purposes. And I need to grab this one up here and console log it and take a look at it, because we have technically implemented a selection sort, believe it or not, with minimal effort. So from here, I'm going to save this and see if it runs. 11, 12, 22, 25, 34, 64, and 90. We do indeed have our sorted array using a selection sort. Remember, the bubble sort had things bubble up towards the top. The selection sort means we just compare and then swap at the end. So once again, outer loop will be incrementing after each sorted book as we go from smallest to tallest. We make the assumption that the current book at the beginning of our unsorted part anyway is our new minimum. We then take that current minimum and look at every other book on the bookshelf and compare. If we find a smaller book, we mark that down. At the end, we say, hey, if we've made any changes on the smallest book, that means we found a new small one, and then we swap those positions. And then our new smallest book will be on the left-hand side. We increment over one to next to that, and then do the exact same thing. And we repeat that until the whole array is sorted. You could also do, I think I've shown this in previous videos, you can do like a cool ES6 style swap where we can do the following. Nope. I never get this right the first time, because it's hard to look at. Yeah, that's right. This is what we do. That's also like our ES6 cool kid swap right there that we can also take into consideration. That's another way we can swap it. I'm going to save it and make sure we get the same output. We do. That's what I'm talking about. So, yeah, that's the selection story. Also, as always, we got to talk about a couple things about it, because again, like the actual code, is less important than what I'm about to discuss here. So, the big O. How about we talk about the big O? So the big O complexity on this one is n squared. I think at this point in this playlist, anytime y'all have seen any kind of nested for loops, we can say n squared time complexity. And just like in bubble sort, we also have a space complexity of 1, because as you can see here, we sort in place and it doesn't produce, it doesn't have a new variable or new array we are creating. We just sort the array we are given. Therefore, it doesn't take up any additional space. So we have a space complexity of big O of 1, which is just a flat line. And then n squared, remember, is that exponential curve on our friend, the big O picture. That n squared right there just goes, right? Because the bigger our input gets, we have to loop through everything, right? It is a n squared complexity pretty much anytime we have this double for loop happening here, right? Because The outer loop runs n times, where n is the number of elements in the list, and for each iteration of the outer loop, the inner loop also runs n times. So that's where we end up with n squared. Yeah. Selection sort is pretty efficient, right? It's in-place sorting, which is why it's a big O of 1. So in terms of, I guess, pros and cons, it's simple, just like the bubble sort. I think that's a pro in these sorting algorithms. If it's simple to write and implement and understand, that can be a boon depending on what your needs are. It is memory efficient. It sorts in place, meaning we do not create any new variables. It's a constant big O of 1 for extra space required. It is very performant for small data sets because it can be faster than the more complex sorting algorithms on small data sets. And remember from the bubble sort video, we did a crap ton of swaps. But if you haven't noticed, this one only swaps a singular time after the iteration is complete. So this is a good one to know when the cost of or computation of swapping is high, like in bubble sort, because we kept on swapping things over and over again to have that the biggest one bubble to the top. Whereas here we simply pick up a book and then run comparisons, right? That is much more efficient than swapping constantly. We only swap at the very end of all comparisons. So it's a minimal in terms of swapping. But with efficiency, again, if n squared, it's pretty bad the bigger your list gets. So if performance is an issue, probably not one you want to go with. You want to go with insertion, quicksort, heap, stuff like that. But again, that'll be later in this series. Yeah, so it's not what am I going to describe this? Like it unlike some of the other ones, selection sorts don't adapt to the existing order of an input list. It's going to perform the same number of operations whether the list is partially or entirely sorted in reverse order. So like it's not going to adapt well to things that are partially sorted like our bubble sort could, right? So yeah, I mean, like I said, the pros and cons are pretty obvious here. Like small number of swaps, performance for small lists, very memory efficient, simple to code. N squared performance for time complexity, meaning the large data set's probably not the way to go, and it does not do well with data sets that are already partially sorted or reverse sorted, things like that. It doesn't check for those things, and it will do all the comparisons regardless, right? So there's really not, outside of like knowing this for interviews, I can't really give you like a bigger picture of where this is cool. It's just good to know for practicing your problem solving skills, passing interview questions that you may get thrown your way. It begins to have you think of efficiency. So thankfully, some of these sorting algorithms I've covered in this playlist so far, their code is never that bad. It's more about considering their pros and cons. So that's important to know about this one. And, again, having more tools in your tool belt is always a good thing. So comparing to bubble sort and selection sort, they both pretty much have a big O time complexity of n squared, but the performance can be quite different just because bubble has all those swaps, making it generally slower than the selection sort, which performs at most n swaps. But bubble sort does have the ability, like I said, has that adaptability. It can stop early if the list becomes sorted before all passes are complete, which can make it faster. So if you know your data set is partially sorted, you can go with bubble sort. Otherwise, you can go with selection sort. They're both in-place sorts, so there's really not a whole lot to consider there. And again, you never really use them for large data sets, but just understanding that do you have something partially sorted and are swaps expensive or not is basically the question you ask yourself between using a bubble sort and a selection sort. And just like in the previous video, I would like to draw us to our friend Timo Bingmann on YouTube, where I muted out the sound here. So if you want to hear the sound, you have to get this link yourself. I'll try and include it in the description down below. But just like we visualized the bubble sort, we're going to visualize the selection sort. And it starts out pretty slow, I'm not going to lie. So you can see that red flashing over here. That is our smallest element we have seen so far, and it's running all these comparisons. After the comparisons are done, it's going to move that smallest one to the left, and then do the same thing. Then it's going to assume this book as our smallest one until it finds this one, and then it's going to memorize that position, make all the comparisons, and now you can see it slowly picking up speed, right? But this is the visual. This is exactly what our code is doing. It is running all those comparisons, swap, running all the comparisons, looking for the smallest book so far. There it is, swap. Find the smallest book so far, swap. And it's going to continue. I know, like, I don't want to fill dead air for another 30 seconds, but I want this, like, I don't want to ruin y'all's day by not showing you the final whoop staircase that this thing finally builds, or rather, organize books on a bookshelf. But yeah, like I've been just saying over and over again, the number of swaps is way smaller, which is a huge boon to this one compared to bubble sort. But again, if you have something that's slightly already sorted or reverse sorted, or the second half is already sorted, it's not going to matter. This will have to make all the comparisons regardless, whereas bubble sort could stop early. And we're almost there. Smallest one, let's go. And boom. We got it, y'all. So that is selection sort. No test on this one because, again, it's just like taking a look at our logs here. Clearly shows us that we have sorted the array as intended. Your choice on whether you use the cool ES6 swap, ES6 array destructure swapping shenanigans, or you use your traditional just temp variable. But either way, I appreciate y'all for watching. Hopefully this has been helpful in our journey together of becoming better developers. If you enjoyed this video, give it a thumbs up and consider subscribing to the channel for more videos like this. I'd love to hear y'all's thoughts on these algorithms. Like with these, I don't think you can really provide a lot of alternative solutions minus shorthands or efficiency optimizations. There are some cool things you can do by declaring multiple variables and things like that. But remember, constructive and positive comments are the ones that are always welcome here. So let's keep this discussion going and help each other improve our coding skills. So thank you for tuning in, and I'll see y'all in the next video.